Hello, I would like to talk to you about matrix factorization for high-frequency non-intrusive load monitoring. The goal of this short paper is to introduce high-frequency NILM from a machine learning point of view, and especially a matrix factorization formulation. The key points of this paper are first to present the matrix representation for high-frequency current and voltage measurements. Secondly, we show how to transform the general source separation NILM problem into a matrix factorization one. And finally, we review existing methods to solve this problem. To construct the matrix, we simply take the values of the current and voltages during one voltage period and put it in the columns of the I and U matrices. The power is then calculated as a simple dot product. Here are 4 examples of current matrix measurements for individual devices, such as lights, microwave, air handling unit, and hair dryer. Let's go back to NILM and its source separation problem. By the Kirchhoff current law applied at the main breaker level, the total current denoted by capital I main is equal to the sum of the current of all the devices. The source separation problem on current is then defined as estimating individual current denoted by capital IC from the observation of the total current. This problem can be turned into a matrix factorization one. To do so, we first need to introduce the rank 1 approximation hypothesis. It says that the current matrix of an individual category of device can be well approximated by a rank 1 matrix, defined as the product of one column vector, called signature in green, and one row vector, called the activation in red. Recording that the total current is equal to the sum of individual current I of C, we can then write it down as a matrix factorization approximation problem, where the total current matrix I is factorized as the product of a signature matrix S and an activation matrix A. Note that each column of the signature matrix corresponds to one and only one category of device C, such that the number of columns equals to the number of category of equipment. The NILM problem is then to estimate the S and A matrices from the observed I matrix, such that the product S times A approximates well the observation I. Once the total current is approximated using the signature activation factorization, the individual power consumption, P of C, can be recovered using the power formula. In the paper, we review existing methods to solve the NILM problem as a matrix factorization one. Please do not hesitate to get in touch if you have further questions. Thank you for your attention.